Welcome, class. I'm just opening up chapter 2 with just a summary of some of the atomic models that we have over history. And this is just going to give you a little bit of an idea of where we've come from and where we are right now with understanding atoms. We're not really looking at the periodic table so much here, but in the background we're kind of thinking about how eventually we have the periodic law and the organization of elements in the periodic table. Kind of starts with a bit of an understanding of the types of knowledge that we have in science. We have theoretical knowledge, which can be ideas or images or maybe models that can be created. They're non-observable, and yet we have the opposite, which would be empirical, which is based on experience and experiment, which are observable. And it's sort of this interaction between the empirical and theoretical. Sometimes the theories lag behind a little bit from the empirical in that we haven't yet observed what we predict. Sometimes we have technologies ahead where we're creating things that we don't quite know how to explain with the science, and yet they're useful. And so there's progress and development with technologies. Scientific knowledge kind of fits into those two types, and there's lots of different ways we can map this with a sort of a concept map or a mind map. We have tables of evidence, graphs, descriptions, concepts. We can make hypotheses before we do experiments, make definitions based on things that we see. We can generalize and make laws such as the law of gravity. So this is one arm of the scientific knowledge. And then, of course, theoretical, we have our models, theories, analogies, which are often useful to help us to understand something that we maybe haven't observed yet. So some of the models over time can kind of be looked at just sort of at a glance, sort of sweep through here and highlight some of them just briefly. We have the early Greeks theorized that matter is composed of very small indivisible particles. That's where the name atom came from. Atomos, which is not possible to cut. You can't cut it anymore. That was the theory that Democritus came up with, 5th century BC. Aristotle, 100 years later approximately, had this four-element theory of matter, which is shown in your textbook on page 24. It kind of has water, earth, fire, and air as a model for matter. And then we have sort of a long period of time where history, anyway, doesn't record much in the way of theories or models of matter until about the 18th century. John Dalton does some pretty good science and comes up with two laws: conservation of mass in chemical reactions and constant composition, which we'll look at in this course as well, which generally just states that in a particular compound, the mass ratio of the elements is always constant. Okay, John Dalton also understood, or at least theorized, that all elements must have unique mass, unique size, and a unique set of properties. Okay, there's some other models which more recently have added, or as recent, or within at least the 1800s and 1900s, have added to our understanding of science. We have the J.J. Thomson model. Rutherford's is well known, and Chadwick as well. You can kind of look at maybe Rutherford's first, and he's famous for this gold foil experiment. The gold foil experiment, kind of show you a little YouTube clip here to help you understand it.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source was aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
Okay, so Rutherford, he is probably best remembered for his work with the nucleus. And when we look at Rutherford's theory, it's small positive nucleus surrounded by electrons, no neutrons yet at this point, but definitely positive charge containing much of the mass of an atom. Now, Chadwick later discovered the neutron, and that added a little bit more to the understanding, with all of the mass of the atom accounted for. The electron was probably known much earlier than that. So we have, before the 1900s, we had J.J. Thomson working with cathode ray tubes and understanding that, well, there's negative charge within an atom. He had no concept of the proton or the neutron or their masses, but certainly that there was some positive charge there, and these electrons were perhaps distributed throughout. So let's have a look just at his work a little bit more.
A cathode ray can be deflected by an electric field. The beam is attracted to the positively charged plate.
Okay, so cathode rays, actually up to probably maybe 10 years ago, cathode ray tubes were what powered televisions, and now with flat screen televisions and LED screens, we have quite a bit different technology, but the CRT, or cathode ray tube, just simply a stream of electrons which can be moved around by electrically charged plates. And of course you saw there in that animation how the stream of cathode rays were attracted to the positively charged plate. So scientists knew enough about batteries to understand positive and negative potential, and they saw that the stream was deflected upward, which indicated that the particles in this cathode ray had mass and also must have been negatively charged. So that led to the discovery of the electron. So Thomson's theory is called the Reisenbund model, which is because it was just a uniform distribution of negative charge. So we've had Rutherford's theory as well, and Chadwick's added a little bit to it. The other models, which are a little more recent, include the Bohr model, which includes the knowledge of the electrons and their position in an atom, and also the quantum model, which came a little bit later in the 1900s. Okay, so just to close, let's just get a summary of atomic structure as we understand it. So the name of the particle, its location, actual and relative masses, and relative charge. So this is review a little bit as well, but we have the proton with positive charge. It's located inside the nucleus. Its mass is given in grams, very small number. We would prefer to actually call it 1 on a scale of relative mass, about 1 atomic mass unit as well. We'll see that unit coming up in the next video on atomic mass. And a relative charge, positive 1. The neutron having a relative charge of 0, it's being a neutral particle, slightly heavier than the proton, also located inside the nucleus, and again, because it's so close in mass, it's still relatively 1 on a scale of relative mass. And finally, the electron, located outside the nucleus, very, very light particle, having a relative mass of approximately 0, relative charge of negative 1, and we can see that the relative mass is about 55 10,000ths of the mass of either the neutron or the proton. So it's because it's so small, it's considered to be 0. Some assignment work which you can have a look at just to bring your knowledge up on some of these things, which you saw in grade 10, 1 to 5 on page 26. And if you're watching this video as just a review, then you can return here anytime if you're looking for just a reminder of some of these things. I'll see you in class tomorrow.